Welcome everyone to 11.2 series. Now chapter 11 is called Infinite Sequences and Series, and you can see how fast we're done with infinite sequences. So the rest of the chapter, from here section 2 all the way on to section 11 essentially, is going to be dealing with series. Now series is this interesting idea of adding together infinitely many numbers. And if you were to just take, any random set of infinitely many numbers and add them together, it wouldn't head towards anything finite. So for instance, if I just took 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, right, this is going to keep on getting bigger and bigger and bigger, and it's not going to head towards anything finite. But sometimes, if you take the right set of infinite numbers and you add them together, it does actually head towards something finite. And these are very interesting series. So in this section, I should probably formally define what are series, and we'll go over some different types of series. And then we're going to try to figure out when do series actually converge towards a finite number versus when do they diverge and head towards infinity or negative infinity, or just they never head towards anything. All right, so let's get to it with a definition. So in general, if we try to add the terms of an infinite sequence, a sub n, we get the expression of the form, well, let's go ahead and add these things. a1 plus a2 plus a3, and it keeps on going forever. We'll include an, and it just keeps on going. So this is called an infinite series. So that's the new thing for the section series. Sometimes instead of infinite series, you just say series. And we can denote it by the sigma notation. So we're going to say sigma, or the sum, as n goes from 1 to infinity of a sub n. So here's our a sub n, and n is going to range between 1 to infinity. Or if you'd like, you can just say the sigma, or the sum, of an's. And if you don't include the subscripts, we'll assume that it goes from 1 to infinity. All right, so let's go ahead and define here. Suppose we have a series, and then we're going to denote this thing S sub n to be the nth partial sum. So S sub n, we could write down a formula for this thing. This is going to be the sum from I equals 1 to n of a sub I. So here's my a sub I, and I is going to range from 1 to n. So that is a1 plus a2 plus all the way up to an, but then it stops. So that's the nth partial sum, is that it actually stops. It's not an infinite series, but it's finite. So if this sequence of partial sums is convergent, we say the limit of n approaches infinity of s sub n is equal to s, exists and is a real number, then the series is called convergent. So we'll say that this actually converges or heads towards something. So that's pretty exciting. And then in that case, we would say the series, so my a1, a2, a3, all the way to an and beyond, is equal to s. Or if you'd like, using the sigma notation, the sum from n equals 1 to infinity of an is equal to s. So in general, s is usually called the sum of the series. And if this sequence is divergent, then the series is called divergent. So again, the sequence is divergent, then the series is called divergent. Okay, so let's go ahead and take a look here. Determine if the following converges or diverges. 1 plus 2 plus 3 plus 4. And so let's go ahead and kind of practice looking at these partial sums. So S1 is going to be the sum of just the first term, so that's 1. S sub 2 is going to be the sum of the first two terms, so that's 1 plus 2 is going to be 3. S3, the third partial sum, is going to be the sum of the first three terms. 1 plus 2 plus 3 is 6. S4, I think you kind of get the pattern here. S4 is going to be 10. S5 is going to be 15. And so you see that we're building kind of a new sequence, a sequence of partial sums. And so the claim is this seems to be getting bigger and bigger and bigger and bigger. So our intuition should say that this series diverges because the sequence of partial sums gets bigger and bigger and bigger. So it looks like it diverges. If we wanted to prove this with a little bit more rigor, I should note that S sub n we could actually find a formula for, and this is equal to n times n plus 1 over 2. And of course you should be skeptical. Let's go ahead and double check and make sure that this at least lines up with our first few values here. So in our first case, if I was to plug 1 into this thing, so 1 for my S, so I would get 1 times 1 plus 1, so that's 2, over 2, so that's 1. How about 2? If I plugged in 2 into my formula, well, let's see, 2 times 3 over 2, that's going to be 3. How about if I plugged in 3 into my formula? 3 times 4 over 2, that's going to be 6. So it seems to be working. Seems to be working. So now if I took the limit of this partial sums, n times n plus 1 over 2, and I let this get very, very large, well, this is going to head towards infinity. Right? As n gets large, the partial sum head towards infinity. So therefore, we've shown that the series diverges. Okay, now we have a different series, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And my claim to you is that this one actually converges. And to show you that it converges, I'm going to draw a picture. So I'm going to be thinking about pi here. So here's 1 pi, and I'm going to add to that half of a pi. So here's my half of a pi. And then to the same picture, I'm going to add a fourth. So a fourth of a pi, which is half of the remainder. And then I'm going to add an eighth of a pi. So an eighth is going to be half of what's remaining still. And then 1/16. 1/16 is going to be half of what's remaining still. And then 1/32. And then 1/64. And then so on and so forth. Forever and ever and ever, keep on adding this little bit, but it never seems to quite hit all of the next pi, right? It gets very, very close as you would want, but never quite get there. So the claim is that this is actually equal to 2 in total. So we have our first pi, and then we have all of these little fractions that will add up to be very, very close to another pi. So the series, the sum from I equals, and I'm going to do 0 to infinity, of 1 over 2 to the I is equal to 2. Right? Because we start off with 1 over 2 to the 0. 1 over 2 to the 0 would be 1. So that's why we're starting at 0 here instead of 1. Okay, so this, as it turns out, is a special type of series. And so that's my next definition here, is that this previous series is actually called a geometric series. Maybe that's why there's a nice picture here related to it. So a geometric series. So in general, these things look or have a certain form. There are a plus a times r plus a times r squared plus a times r cubed plus a times r to the fourth, so on and so forth forever and ever. So another way you could write this is the sum, and this time our series is going to be starting at 0, of a times r to the n. So the geometric series, and let me go ahead and I'll just copy and paste essentially what I have up above. The claim is that we can actually figure out when this is convergent or divergent. So it's convergent when the absolute value or the magnitude of r is less than 1. And in that case, we can actually find what its sum is. Now let's remind ourselves, this absolute value business, this is the same thing as r is between -1 and 1. So in that case, again, the series converges, and it converges to a over 1 minus r. So that's pretty exciting that we can actually figure out what this converges to. Then if the magnitude or the absolute value of r is greater than or equal to 1, then the series diverges or is divergent. So let's go back up, and I'd like to go ahead and prove with a little bit more rigor now that we have this nice theorem about that this thing actually converges towards 2. So our a is always our first term. So a in our case is 1. Now r is going to be found by the second term, right? Because we know a times r has to be the second term. So in our case, we have a times r needs to be 1/2. So here's my a, and I don't know what my r is. Well, I can quickly solve for r in that case and figure out that r has to be equal to 1/2. Okay, now go ahead and plugging this into my formula, we know then that the sum from n equals 0 to infinity of a times r to the n, so that's 1 times 1/2 to the n. Another way you could write this, distributing the n to both the numerator and the denominator, well, 1 to any power is going to be 1. So it's going to be 1 over 2 to the n. This is equal to, and according to our formula, this is a over 1 minus r. So simplifying this down, we get 1 over 1/2, and instead of dividing by a fraction, let's go ahead and multiply by the reciprocal. All right, and that's probably a good place for us to take a break here in 11.2. As you can see, with geometric series, we know pretty much the entire story. We know when they converge, we know when they diverge. For just your random old series, it's a lot more difficult. So when we come back, we'll go over a theorem for telling us when a series will diverge, definitely. And then we have more examples. So I'll see you in a little bit.